Well, thanks everyone for coming. It's a great honor and pleasure to have Professor Georg Bruun here. Like he's a recipient of our prestigious Cátedra Eisen-Demoshinsky. So we are really happy to have you here. Like we have had like very exciting lectures with our students and with our collaborators. So before we start, let me just say some few words about Professor Georg Bruun. So Professor Georg Bruun got his PhD at the University of Oxford. Then he did a postdoc at the University at the NIST in Colorado, right?
Yeah, no, in Washington.
Washington, yes, Washington. Then he got a assistant professorship at the University of, at the Niels Bohr Institute in Copenhagen, to move next to Lund in Sweden. Since 2010, he has been a professor at the Aarhus University, and he specialized in quantum many-body physics. In particular, he has been pioneer in the Polaron experiments and collective modes in atomic gases. And he has also moved now to polariton and quantum materials in low dimensions. So thanks a lot, Georg, for coming here.
Yeah, so thank you very much, Arturo. And it's like Jacopo yesterday, I will say that it's fantastic to be here in Mexico City. It's my second time, and it's really exciting, both to try all the, now also earthquake, but also scientifically, I'm very impressed with what I've seen here. It's really becoming an active center, or maybe it has been already. And before, the talk has changed. Actually, the title of and content of my talk has changed due to some of the discussions I've had here. So last night I was changing the talk yet again, because there's so many exciting things going on here that I'm trying to link some of the stuff that we did to what is going on here. So what you see here is the overall theme is, somebody asked me before the talk, what is this cartoon here? These are atoms, in this case, which are Cooper paired. I'll get back to that, in a two-dimensional trap. So this is one of the topics of the system. This laser beam here, I'm actually not sure what that means. So but it's supposed to just be a two-dimensional trap with some atoms, and they're Cooper paired. That's what this means. Before I start, I want to thank Arturo and Miguel. I mean, they were my postdocs in Aarhus a few years ago. And this is yet another positive consequence of their stay in Aarhus. I mean, they were excellent postdocs. First, I hired Arturo. And then I think a year later, I hired Miguel. And they were fantastic postdocs. It was very productive scientifically. And you will see their names pop up throughout the talk. And typically, it would be such that I would discuss with one of them, let's say Arturo, and then he would go into the neighboring office where they both were sitting. Whoops. And then I could hear them speak very loud in Spanish. And I don't know whether it was positive or negative, but the physics that came out was always good. So I hope this collaboration, of course, will continue. But I'm grateful for them to invite me here. And I'm also super happy to get this Mushinsky prize. And also, as you will see, the name Mushinsky will actually appear in the talk. I've actually used his research. So maybe some of you don't know what he did and who he was, but I actually know from my early days as a postdoc. So the outline of the talk is connected to this picture here. So this is the emerging of a quantum phase transition with increasing particle number. And this is work that goes way back, but it's continuing actually. So I'm going to show you some unpublished data. And this is these Cooper pairs in mesoscopic systems. And this relates to what, if some of you were at Jacopo's talk yesterday, how many particles do you need to be in a thermodynamic limit? Apparently, according to Landau, you need 10. It seems to be more or less the right number also in this case. And here is where Mushinsky turns up. Then I will talk about, and this is I put in because it turns out that there are very nice experiments here where people are planning to collide polaritons in a CERN a kind of experiment, a collider experiment. And this is actually something we worked on, both Arturo and Miguel and I, and we called it the CERN experiment, the CERN paper. That's what we refer to this. I will tell you what we did here. So this is actually directly relevant, hopefully, to some of the experiments going on here. And then if time permits, but I don't think I'll get time, then I will also talk about some, because people also seem to be interested in topological systems here, how to probe edge states with polarons. But let's see whether we get that. This is a very recent work. So let's get started. So let's get back to how many, this thing about the thermodynamic limit, how many particles do you need to be in the thermodynamic limit? And this is something that actually the ancient Greeks were thinking about many things. And it's actually quite impressive, but one of the things they were thinking about is now referred to as Sorites paradox. And this is the idea that you take a grain of salt, or sand actually in this case, and you add, here's a grain of sand, you add another one, you have two, you add another one, you have three. But then at some point when you have enough, you get into this material called sand, this plastic material that you can build sandcastles with, and you can build a wall, or you can dig holes in it and so on. So they were worrying about how many grains of sand do you need to get this emergent property here. This is somehow a material which has collective properties, and over here you just have individual grains of sand. And this is something you can see many places in nature. So another, just to go over here on the other side. Another case is very qualitatively, if you have a single bird, it's a nice single bird, but if you have many of them, I don't know whether you have this phenomenon in Mexico, but in Denmark we had this phenomenon called black sun, where these birds, when they migrate in these clouds like this. It's very impressive to see. So suddenly this collective behavior emerges when you add more and more birds. To get a little bit closer to physics, another example is water molecules. You have a few water molecules. How many water molecules do you need to get water that can freeze and evaporate and so on? These properties over here would be very hard to predict from just looking at one or two water molecules. And this thing that something new happens when you add more and more particles has been formulated in a nice way by P.W. Anderson, who was a famous condensed matter physicist. He has this highly cited paper where he says more is different. So this was an answer to this reductionism in elementary particle physics, where they say you have to go to higher and higher energies, and to get at the only interesting stuff happens when you look at the elementary constituents of matter. And he said, oh, that's not true. A lot of interesting stuff actually happens when you go to the thermodynamic limit, when then some new qualitatively different stuff emerges. And what we refer to here is more precise. Is when we have a system, we go to the thermodynamic limit, keeping the density constant. These new effective low energy properties emerge, which we can describe as physicists with effective theories, where you don't worry about the properties, what each individual particle does. You can reduce it to a few variables, for instance, pressure, temperature, and volume. And then what the first part of the talk will concern is how many particles do you need to see these collective properties emerge. And what we will look at a specific example, which is superconductivity. But to illustrate what that actually, basic physics of that is, it relates to, we will look for spontaneously broken symmetry. When does that emerge? So it's a collective many-body phenomenon, and we will look at when does that happen. So a good way to think about it is if you have a single compass needle and there's no magnetic field, the needle just points in any random direction, it rotates around, it's highly unstable. If you have many of them, then they tend to below a certain temperature, at least in 3 dimensions, and in 2 it's 0 temperature, but they tend to align in a certain direction. And the way that we like to describe this is, again, this name Landau. So he will say that that's because it minimizes it. So you have the free energy as a function of the magnetization. When the temperature is above the critical temperature, the magnetization is 0. There's no reason to spontaneously align, but then when you go below the critical temperature, the free energy is minimum at a finite magnetization. But you have rotational symmetry, and this is very appropriately called the Mexican hat. So I don't know whether this is, I put this in this yesterday, and that means because you have these needles can point in any direction they want. Oops. So this minimum free energy landscape is actually this Mexican hat potential. So this is just the direction of the magnetization. So connected, so they can pick any direction they want, and connected to this, there are low energy collective modes. So there's these things called Goldstone modes, where you get these spin waves where the magnetic spins circulate around. But there's also this amplitude mode, which is called the Higgs mode. And this is the latter one we will study. And we will study it in the context of a superconductor. So I'm not sure how many of you probably know this, but let me. So what we will consider is fermions, two different kinds of fermions, spin up and spin down, red or blue, which interact with each other attractively. And then what happens is that below a certain critical temperature, they form Cooper pairs. And these Cooper pairs are bound states of these two kinds of fermions. And what happens is that this bound state wave function has a phase, but the phase between the different Cooper pairs, the phase of this wave function, this phase function, this wave function locks. So they pick a specific global phase. So they also break the phase symmetry, this U1 symmetry, just like up here. And what we will look at is how many fermions do you need to see this spontaneously broken symmetry. This is related to, and now it's where Muschinsky comes in. So we will take a two-component Fermi system, and we will look at pairing, and then we'll add more and more particles, and then we'll see when this BCS picture works. And this is something that has been studied in nuclear physics, which was very strong here. Maybe it still is. I can see that it used to be. And this is because the neutron and the proton pairs. But there are not that many neutrons and protons, so it's also kind of a mesoscopic system. Is it really in the thermodynamic limit or not? And this is how I got into the game many, many years ago, because I was a postdoc in Copenhagen, where this is the way back when these ultra-cold atoms first came about. And these are ultra-cold atoms are what they could do, for instance, would be to trap fermionic atoms in two different kinds of fermionic atoms. They could play with the interaction strength, but they're typically confined in a harmonic trap. So that you can start worrying about what is the pairing between these fermionic atoms in a harmonic trap. And this links to the nuclear problem, because the nuclei form this harmonic potential by themselves. It's a little bit different. Here it's exposed from externally, but it's pretty much the same problem, just simpler over here. So that's why I started to work with him. Ben Bottleson, who actually got a Nobel Prize for looking at this kind of stuff. So this is how I got into the game. And during my work, I actually used Muschinsky. So some of his work is called Muschinsky brackets, which tells you about how you change from individual particle coordinates to relative and center of mass particle coordinates. I remember I looked up his paper, and I noticed that he was from Mexico. So I sort of checked up who this guy was. So it's funny now that I'm speaking on this on behalf of this Muschinsky Prize. Good. So a lot of the work we did was actually irrelevant in the beginning, because the cold atom experiments were thoroughly in the thermodynamic limit initially. But then along came this guy from Heidelberg, Selim Joachim, who can actually make these small systems, these mesoscopic systems. And so now a lot of the stuff that we did back then is actually becoming relevant now. So now they can actually check what happens when you have a few fermionic atoms and they pair up. Okay, so very quickly, so what we will look at is pairing in a two-dimensional trap. And you can look at, so you have these two components, spin up and spin down, and they interact with each other attractively. And we will be in 2D because that's what the experiment is. And there are two kinds of, so if you check, so they like to pair up the spin up and spin down fermions, and they can pair up. So this green fermion can pair up with a fermion from another harmonic oscillator shell. That's called intershell pairing. Or it can pair up with a fermion from the same shell. That's called intrashell pairing. And in the usual case, in the initial experiments are always in the limit when the pairing energy, we're all in the limit where the pairing energy, the binding energy essentially, was much larger than this level spacing. That means that predominantly the pairing just occurs across all shells. And the size of the Cooper pairs, the size of these bound state wave functions, is very small compared to the size of the system. So you can just do local density approximation, and all the textbook theories work essentially. But if now you go to these microtraps, then you can go, there's Selim-Joachim studies, you can go to the limit where the pairing energy is much smaller than h bar omega. So really, these shells start to matter. And this is the regime I will worry about here. And there you get only pairing within shells because it's too expensive to start pairing across shells. A little bit of theory for those of you who are condensed matter who like this kind of stuff. The way we analyze it is just simple BCS theory, or Bogoliubov-Deschênes. It's the same. So we solve the Bogoliubov-Deschênes equations in the presence of this trap. And what you then can do is you can, if you say, okay, I only have pairing between spin up fermions and spin down fermions sitting in the same shell N, but with opposite angular momentum. So they rotate in it, so they are time reversed, but they sit in the same shell. If you make this assumption, you can actually do analytical solutions. This is where this Ben Mottleson guy comes in, because they have all these tricks. So I use those and generalize them to 2D, and you can just solve this problem analytically. I'm not going to go through the details, but you can actually do a very accurate theory in the regime. If you just assume this is almost as easy as usual BCS theory, where you have pairing between k and minus k, a little bit more complicated, but not much. You can solve it, and you can recover certain regimes and so on. And what I will talk about is two cases. There are two cases. There are two qualitatively different cases. There's one case where you have an open shell. This is also what happens in nuclear physics. So the highest shell is only partially filled. Then for any infinitesimal attraction, that you always get Cooper pairing. So for zero temperature, any attraction gives you Cooper pairing. If you have a closed shell case, on the other hand, which is called magic shell in nuclear physics, then you only get pairing across when the interaction strength is larger than a critical value, because basically it pays. So the closed shells are all rigid. It pays a certain amount of energy to start creating fluctuations across open shells to create these Cooper pairs. So it only pays off beyond a certain critical coupling strength. This is all mean field BCS theory. So we are in the thermodynamic limit. We're using this thermodynamic description, and this I'm just telling you what it gives you, and then we're going to check how well it works. So that means that within this, in this thermodynamic limit, you would expect a phase transition when G is smaller than GC. It's not paired. When G is larger than GC, this coupling strength, you do get pairing, and you can calculate what this critical coupling strength is, and so on. Good. So in terms of this picture you saw before with this Mexican hat potential, it means that when you crank up the coupling strength G, when G is less than GC, the minimum free energy is for zero pairing. When G is larger than GC, the minimum pairing is for finite pairing. That's where you find the minimum free energy. So it has to become soft in the middle. This potential moves into a Mexican hat, and there's some point where it becomes very flat. And the Higgs mode of this collective mode, which people refer to as the Higgs mode, will then get, which is an oscillation in the size of the pairing, in the amplitude of the pairing, will become, the frequency of that mode will go to zero at this critical point. This is a general thing about this phase transition, that a mode goes to zero at the critical point. And then here it starts finding a non-zero average value, and then it can oscillate around that. So this is what we will look for. And you can calculate, you can just then use this intra-shell pairing ansatz, and you can go beyond. You can, to calculate this Higgs mode, you have to look at fluctuations around mean field, and you can do that again using standard techniques. It's a little bit more complicated again, as in the case of usual K minus K pairing, but you can actually get it done. And what happens, so you look at fluctuations in the pairing field. They split into fluctuations in the phase and fluctuations in the magnitude. And we will not talk about, so these are called ghost modes, the ones with the phase. But we will focus on fluctuations in the amplitude. And what you find is you find a well-defined mode. Typically, these Higgs modes are damped in, unless you have particle hole symmetry or Lorentz invariance. But here they are totally sharp and undamped because you have this level spacing. That's a detail for those of you who know about Higgs modes. They're typically damped, but in this case, they're very sharp. So we will look for this Higgs mode, and its frequency is 2 times the pairing energy. This was in the superfluid phase. In the normal phase, you also get this amplitude mode in the order parameter, but now it fluctuates around 0. So it wants to pair, but it doesn't really. It oscillates around 0. And again, you can calculate what the mode frequency is. You can get an expression for it. And the way to think about it, and we will get back to that later when we look at the experiment, this pair fluctuation mode is, if you look at the wave function, it corresponds to, it excites time reverse pairs from the filled shell up to the empty shell. If you look at what the wave function corresponds to, giving you this frequency here, I'm looking at monopole modes. You can generate a monopole mode by going 2 shells up, but this one actually corresponds to excitations of pairs of particles 1 shell up, but time reversed. That's how you build this mode. So this is the prediction. Let's forget about the open shell. So the prediction is, as a function of the interaction strength, you should get this Higgs mode or pair vibration mode. It starts at 2 omega for no interactions. If you take a pair of particles 1 shell up, it costs you 2 times omega. But then it goes down as you increase the attraction. It goes to 0. Now the system wants to be superfluid. The potential is completely flat. And then it goes up again and scales with 2 times delta when you're in the superfluid phase. So this is like a standard picture from a textbook, but in this case, in this harmonic trap. And we're going to check now, how well does that work? How many particles do you need? So what you can also do and this is, I mean, we tried many different things, but at the end, we just gave up, and then we solved it numerically, hardcore, just exact diagonalization to figure out what happens in the few body limit. Because the other thing was mean field plus fluctuations. It's a thermodynamic description. But now let's see, what does few body physics give us? So we just diagonalize the problem exactly. And this is what you get. So here they've looked at, they cannot go to very large systems, but they looked at the first 2 shells are completely filled. And then they looked at the excitation, the monopole excitations of such a system. They put it on a computer. And then they look at the monopole excitations as a function of the coupling strength here. And this is what they see. So just look at first these modes up here are just atoms. If you look at the wave function corresponding to fermions excited 2 shells up, but there's one special mode which goes down. And this is like this few body precursor of the Higgs mode, because it's now, if you look at the wave function, it corresponds to excitations of time reverse pairs. So this is exactly what you would expect from BCS theory. But now it comes out of an exact diagonalization. You can go to larger particle number, and you get that it becomes deeper here. And then you would expect that it becomes deeper and deeper and deeper when you go towards the many-body limit. And this is what we're going to look for. Yes. So here's the experiment. So this is from the Heidelberg group. So they have this 2-dimensional traps, so they can do this experiment. They can create these pancake traps where the atoms are confined, 2 kinds of fermions confined in a pancake trap where you have a harmonic potential in the transverse direction, but they're very tight in the Z direction. And they can actually control by doing some spinning technique. They can actually very deterministically control how many fermions they have in the system. So they can now do this experiment. They can have 2. They can have 6. They can do all these magic shell configurations. Let's see what they get. It's actually going faster than I expected, but okay. So here is an experiment. So what they do is they start with a 3+3 system, and what they do is they modulate the interaction strength. So this actually refers to what they do is they squeeze the pancake trap a little bit more. They do like this, and this corresponds to modulating the attractive interaction between the fermions. So it's like you start vibrating the Cooper pairs. You make them tighter and looser. You vibrate the size of the Cooper pairs, and then you're looking at the eigenfrequency of this vibration. So they do this. It corresponds to increasing and decreasing the attraction in an oscillatory way. And that couples to this Higgs mode. It doesn't, I mean, we had some discussions about these Faraday waves, where it also like it seems to be that you're modulating the coupling strength in the BCS limit. That doesn't couple to density very well. What it couples to these vibration modes of the Cooper pairs, which are called Higgs modes. So this is the experiment, what they do. And then what they see, here's the vibration frequency, and then here is 2. So you would, and here you plot the number of particles you end up with after the experiment. And you have 6, 6, 6, 6. Let's go up. Yeah, you start with 6 particles, and if you vibrate slowly, nothing happens. But then at some point, let's take this one first. You see that you start losing particles. After the experiment, you end up with some particles down here in many of the experiments. So you lost, and that's because one of the particles has been excited 2 shells up, and it leaves the trap because it's not confined up here. It's a bad drawing. It just escapes. So you end up with 5 particles in many of these experiments because basically you hit this resonance frequency of exciting 1 particle 2 shells up. But you also see a lower frequency down here where you don't end up with 5 particles, but you always lose them in pairs. So this mode, when you oscillate the interaction strength with this frequency, you lose particles in pairs. And this is precisely what you would expect from the Higgs mode, right? So that from this pair vibration mode, because it corresponds to exciting a couple of particles 2 shells up, like 1 shell up. So this is the precursor of the Higgs mode. And they did these experiments as a function of particle number. So here's the interaction strength, here's the vibration frequency, and you see these plots as we saw from the theory before, and you see it gets deeper when you increase the particle number. And if you go in, you can sort of identify. You see 2 branches here. That's because the trap is slightly anisotropic, so you also couple to Cooper pairs with a finite angular momentum. Because it's not oscillatory, it's not circular symmetric, so you can also couple to finite momentum pairing. So this thing here tells you the instabilities for finite L equal 2 pairing. And this is the L equals 0 pairing mode. So with this, I mean, you can sort of, they increase the particle number, and then if we get back to how many particles do you need to see this phase transition, this is 3 plus 3, this is 6 plus 6, so it's again at the order of, I mean, if it starts approaching the thermodynamic limit. So this is like this experiment where you saw this few body. So what you're seeing here is a few body precursor of a quantum phase transition. And you see this Higgs mode in like a few body precursor of a Higgs mode. This is an ongoing work. So now it's unpublished data. So I'm still working with the Heidelberg group. So now there's a whole phase diagram of different regimes of pairing. So as I said, if you have the pairing strength is much larger than the trap spacing, you get usual BCS theory, pairing between P and minus P. And you can solve this analytically in 2 dimensions. This is done in this paper here. And you get that the pairing strength is given by the square root of Fermi energy times the square root of the 2-body bound state in vacuum. There's always a 2-body bound state in vacuum if you have an attractive interaction in 2D. And this is what I plot here. Then these lines here mean that now this pairing is equal to h bar omega. And so when the pairing is smaller than h bar omega, you would expect to be in the intrashell regime. And when it's larger, you would expect to be in this P and minus P regime. So this is here. And then when you, as a function of EF and EB, if you make EF small, or if you make the pairing energy, the interaction small, you would expect to end up in this intrashell regime that I discussed so far. And this is what we're exploring now. So if you want to put it into a more general context, it's always pairing between time reverse states. So this is what this Anderson paper, very famous result from him, saying that if you have impurities, it doesn't destroy superconductivity. It just means that now you pair between, instead of pairing between P and minus P, you pair between time reverse states. And so this is an extreme example of this, where the external trap is a kind of a macroscopic impurity that changes the pairing. So what we're looking at now is, so what they can do experimentally I decided just to take this in because I find it interesting. We're looking at these pair correlation functions here, where you say, what's the probability that you have two particles with opposite spin on top of each other, or what's the probability of having a particle with p and minus p? And they can do this just to show you what they can do experimentally. They can make these see these correlation functions just by taking pictures. So they can ask themselves, if I have a particle here with momentum here, this is after time of flight. So this is basically momentum, pictures of the momentum distribution. They can ask, if I have a spin up here, what's the probability I have a spin down here with the opposite momentum? They can do this just by taking pictures. And this is what we are examining now. So this is work in progress. So we take the small system. Here we have making the pairing energy. So we have a 3+3 system again. And if we take a small interaction strength, and then they measure these correlation functions here, and then this is what they measured. And these data changed, but this is the latest ones. And the black line is our intrashell theory. You see, you get intrashell pairing. It works fairly well, and the pairing is mostly occurs. This is in real space. This is in momentum space as a function of radius. What are these correlations? You see that the pairing mostly occurs at the surface. So the Cooper pairing in this intrashell regime is mostly a surface phenomenon, whereas if you go to strong coupling, you start getting towards this thermodynamic limit, or this p and minus p limit, where the pairing is just maximum there, where the density is maximum, which is in the center of the trap. So you can see how the pairing moves from being a surface phenomenon to being a bulk phenomenon when you increase the interaction strength. So this is what we're looking at now. So this is work in progress. And these are the Heidelberg people that I did this with, and these are my theoretical collaborators in Lund. Let's change to the second topic, which is now I squeezed in because of due to discussions with experimentalists here and also with the students. You seem to like this polarity physics quite a lot. And so this is an experiment where, a theory paper, where we worry about what happens if you have two such polaritons and they scatter with each other. And just to, you know very well what a polariton is, but just to, many of you do at least, but it's a superposition of it's a particle which is a superposition of a photon and some matter excitation. And it can happen in two cases. It can happen in many cases, but the two cases that I have been thinking about, and there are people in the audience who've been thinking about this much more than me. But you can realize these kind of strange hybrid light matter particles in semiconductors, where there are mixtures of excitons and photons. Or you can realize them in atomic gases, where there are mixtures of some atomic excitation and a photon. And this is Arturo and Miguel this is a paper that they have been, they have done. So now I will, because we're talking about scattering, the most natural place to look at this is in atomic gases. So we are now not looking in these cavity systems. We're just looking at laser beams that go into an atomic gas and creates these polaritons, which propagate, and then we will see how they scatter. And this is again connecting back to what many of you heard from Jacopo. This is connected to interactions between photons. So as Jacopo very nicely explained, this is in a vacuum. This is very weak because it's highly off-resonant. It has to create this particle-antiparticle pair. It doesn't have enough energy for reasonable frequencies. But one of the nice things about binding the photons to matter excitations is, of course, that the matter excitation interacts in this case, it would be atoms. They interact with each other, and then you can make the photons interact via the fact that they are bound to the atom. So you can get an effective interaction between the photons. And this is this thing that has been pushed, I mean, very much by Jacopo, who's here, who's really, this is this idea of quantum fluids of light that he has been very much a driver of. So what you would intuitively think then is that if you have such a polariton, so it's partly photon, partly some matter excitation, then the interaction since it's only via the matter excitation, you would expect the interaction of this object here to be smaller than the direct interaction between the atoms, because it's only part atom. It's part atom, part photon. But you would expect it to be, it cannot never be larger. But what we will find is that it can be much, much larger, which is very weird. So if you start hybridizing your atoms with light, two of these things interact much, much stronger than the atoms interact with each other, which is weird. It's surprising, at least. And this is what we are going to, I'm going to tell you now why this happens. And actually, you will get, for those who are experts, you get that the effective scattering length of this process here, you can get that it scales as 1 over the scattering length between the bare atoms. So the smaller this is, the stronger this is, which is surprising. So this is a very busy slide. I'm not going to go through it, but it's just for I know there are experts in the audience who actually, I mean, I had to remind myself about this very complicated, all these degrees of freedom, but it's basically a lambda scheme. So what we are doing is we have a photon coming in, which can couple, which can excite from an atom from a ground state here. And I assume these atoms, I'm not talking about any Doppler effects or any, so they're all in a BEC. So they have zero momentum, they just sit here, but then this photon can come in and it can excite up to this excited state, but it doesn't have enough energy to do it. There's a little detuning here. It's not little, it's large, but it doesn't. But then you also shine on a classical field here, which couples this state up here down to this, between these two states. This state up here is very lossy, but then you shine on this classical field that couples these two states so that you can end up in this state over here, which is long-lived. But the frequency of this classical beam is also off resonant with this atomic transition. And then what happens is that, and I'm going to assume, since I'm in a homogeneous system, I'm assuming that the bare dispersion of the photon is just the speed of light times its momentum. So it's no cavity or anything fancy like this. And then what happens is that, and this is very well known, what happens if it is such that the detuning, if the frequency of the incoming photon minus the frequency of the classical beam is such that you hit this atomic state here, then you're on resonance, you create these dark state polaritons. So these are eigenstates in this rotating frame, which are just, it's a particle that consists only of this red atom, the atom in this red state, and then the photon. They are bound together, and it's very stable because the loss of this thing is very small. That's what we assume, and that's what people have done experimentally. And it propagates very slowly because it suddenly has become massive. So if you've heard about slow light, this is the origin of slow light. So the speed, so the more component it has in this red atom part, the slower it gets. And this is the origin of slow light. But that is the good old polariton. Okay, so I forgot to say, this resonance condition that the photon energy minus this energy from this classical field is such that you directly hit this red atom energy here, only happens for one specific momentum. Because remember, the photon energy has a very steep dispersion. It has a linear dispersion. So if you change its momentum a little bit, then it will be totally off resonance. And this becomes important now. So because you can ask yourself, so what I'm going to ask myself now is, if I put a C atom, if I put a red atom inside this Bose-Einstein condensate of blue atoms, how does it propagate? What is its energy dispersion as a function of momentum? Its energy dispersion as a function of momentum, when it's close to resonance with to this EIT resonance, so when its momentum is such that it matches the energy of the incoming photon in a vacuum, it strongly hybridizes, and it creates this polariton, which has this linear slope, which is the speed of light of this polariton, and that's the one that's very slow. But if you change the momentum a little bit, so you go away from this resonant momentum, where the energy of the incoming photon matches the energy of this red state when you take into account the classical field. When you go away from that condition, because the dispersion of the photon is so steep, it totally becomes irrelevant. So what you end up with is just a C atom, the red atom here, propagating inside the blue C. So it has this dispersion p squared over 2m. It has a little bit of an energy shift here. And that's because you still have this coupling. Whoops, you still have this coupling to the classical field is still on, coupling it to some excited state up here, but it's off resonant. So you can just calculate the energy shift second order perturbation theory, or AC Stark shift. So there's an AC Stark shift of this C atom when it propagates this red atom, and that gives you this energy shift away from zero. Otherwise, it would just be a parabola here like this. And this blue thing here, so what we did was we developed a theory that can describe this transition. We basically just solved it, 3x3 matrix as a function of momentum. And then you get this, and you get this, it's called the spectral function. It's broad because you have loss in the system. So then that's why it has these broad features. So that becomes important now. So now we get back to two of these beasts, two of these dark state polaritons. So they come now in, and we're going to do this CERN experiment, and we're going to see how do they scatter on each other. So these, light beams that they normally go through each other, but will they go through each other now when they're polaritons? So this is what we're going to figure out. So the way we describe this is that we have developed a way to solve this two-body problem exactly in a way that we think is convenient. It's working with scattering matrices in momentum space. So you have two incoming momenta, and then the language that you would describe the scattering process in is you have to calculate the scattering matrix of the two incoming momenta, and they come in with this energy here. So now I'm assuming that I have two polaritons coming in. They're dark state polaritons. They're on resonance, so they propagate without loss, essentially. And now we're going to figure out how do they interact with each other. And we can just solve this scattering process. So since we have solved the one-body problem, we can also solve the two-body problem exactly. So first we solve the one-body problem exactly, then we solve the two-body scattering problem exactly. It's convenient because you can use just those of you who were at my lectures on Tuesday, you can just use this T matrix again to figure out how do these polaritons now interact with each other. And this is what you get. So here there's a lot of parameters in this system, and it's also confusing to me. But what we imagine is we have chosen some interaction between the red atoms, which has a bound state, which corresponds to a positive scattering length between them in a vacuum. So if there was no light, they would have a positive but small scattering length. But they have a bound state. And then we pick some losses and some detuning and so on. And then what I'm plotting here is the cross-section for this scattering process in units of the cross-section of the red atoms if there was no light. So the cross-section of the red atoms is just 8 pi a squared. But let's see that's without light. With light, you see that the cross-section can become huge. It can become 800 times this 8 pi a squared. So by coupling to light, it seems like you can get huge scattering cross-section, even though the scattering cross-section of the bare particles is small. And this was surprising to us, but we are pretty sure that it's correct because it's an exact solution of a two-body problem in the presence of light. And here's why it happens. Let me see. Okay, so it happens for the following reason. So here you have your two, so I'm trying to illustrate it. You have two, think about energy going this way, up here in the vertical axis. So you have two dark state polaritons, they come in with the energy which is equal to 2 times the bare photon energy because they're on resonance. And then you have your red atoms, they have a bound state down here, which is displaced with minus 1 over ma squared, that's the binding energy. So that's the binding energy of the bare atom, the bare dimer. And there's a bound state, this is what we assume. And let's see what happens. So if the light was not on, the red atoms would scatter on each other, but this bound state wouldn't do much because it's so far away, and you would get a very small scattering. But this molecule down here consists of the red atoms in many momentum states. So let's take 0 center of mass momentum. So it consists of momentum states k and minus k up to high momenta, determined by how large is the binding energy. And we saw before that these red atoms, when their momentum becomes different from the EIT condition, they don't care about the photonic part. They just experience this AC Stark shift of minus omega squared over delta. So the vast majority of the wave function that this is built up from is shifted by this energy here. So it's like you have shifted basically the molecule energy by this AC Stark shift. So the AC Stark shift of the molecule is essentially twice the AC Stark shift of each individual atom in the absence of this photon here. And now you can see you can just change, you can now tune this parameter here so that you offset. If you offset, you can tune this parameter here so that you offset this binding energy, and then you get a huge scattering cross-section. And that's because of the AC Stark shift of the molecule you play with. And you play with that by tuning delta omega squared over delta. And that's the effect. So if you want to do these experiments here, if you want to see this effect, you should have a bound state between your polaritons. And then you can shift that with this classical light beam. And then you can, well, if you could shift that into resonance, it's just a very generic feature of a Feshbach resonance. Then you get a Feshbach resonance which massively increases the interaction strength. And then you can go you know, there are many parameters you can play with, but you can convince yourself that you can get to the deeper bound the molecule is, the more you can get, the larger cross section you can get. So if the red atoms in the absence of light are weakly interacting, you can get a very strong interaction by shifting the molecule into resonance. But of course, at some point, it becomes so deeply bound that it becomes unrealistic. You can shift it up. And so that's, if one could do this here with these EIT experiments you have, that would be great. I've tried to convince Jan Arlt in Aarhus to do it, but he doesn't have this Feshbach resonance available to him, unfortunately. But we think, Arturo, me and Miguel think that this should be done because it's a solution to a two-body problem. In this case, the interaction is short range, so it's not a Rydberg interaction. So it's more complicated for a Rydberg interaction, but the generic effect is if you have a bound state, we think it should be there, this effect. Then, good. So then the last section, how much time do I have? Like 10 minutes? 10 minutes, yeah. So very quick. It's just also to tie back to what you also heard from Jacopo about edge states. So here what I'm going to do is I'm going to marry polaron physics with edge states, but in a simpler, much simpler system than these anyons. So, so just as a recap, so these topological phases are, you know, they are nice. They attract a lot of attention both in solid state physics and also in cold atoms, because they are more, they have many funny characteristics, and they are much more normal in nature than, or you know, they occur more often in nature than you would expect, and they are characterized by the fact that they have these edge states. So they have excitations that if they are confined to vacuum, for instance, or some state that has other topological property, there are these edge states. And what I will look at here is chiral edge states. So edge states that if you break time reversal symmetry, they propagate in a certain direction around the edge of this sample. And what I'm going to do is, as Arturo said, I worked a lot on polaron physics, probably too much. And this has to do with the problem of quasi-particles in many-body systems. So if you add an impurity to a many-body system, what are its properties? And this has been studied a lot in atomic physics because you can tune the interaction between this impurity particle and its surroundings. And in this way, you can create this quasi-particle. You start with a bare particle, you increase the interaction, then you end up with a quasi-particle due to interactions with the environment. And this has been done where the surrounding environment has been an ideal Fermi gas. and you can and there are theories that can describe this very accurately. It has also been done where the surrounding environment is a BEC, and here it's basically away from weak coupling. It's pretty much an open problem what the properties of an impurity in a BEC is. We will leave that aside because here I'm going to talk about fermions again. But recently there has been quite a few papers, and also by that's you. That's the one you talked about yesterday, right? Yeah. I just realized, I hope he was there. So there has been quite a few papers now saying, how can you probe edge physics with this kind of impurity physics? So yours was not edge physics, but yours was this non-abelian stuff. No, not abelian, but this Annian stuff. What I will do is, these are about bulk properties of the topological system, so Chern numbers, Barry curvature, and so on. Here I will have a little bit of a different angle, a simpler angle. I will just look at how can I probe edge physics with this impurity physics. So what I'm going to do is I'm going to put the impurity on the edge. I have some topological system which has an edge mode, chiral edge mode circulating in a certain direction. I'm going to put the impurity here, and I'm going to do my usual polaron tricks, and I'm going to see what happens. Can I use the polaron as a quantum probe of this edge? So here's the general setup. I have my Chern insulator, for instance, which is a topological system with a chiral edge mode going in this direction here. And then I'm going to put my impurity here. I'm going to do this. And then the impurity, I'm simplifying the problem so much. So this is only allowed to move here. It's not allowed to move into the bulk. So the impurity can only move here. And then I'm going to see how is this affected by this chiral edge mode. So it's by construction. I'm making a system that is sensitive to the edge mode. So it interacts with the majority particles here on the edge, but it's only allowed to move on the edge. So it has this point interaction. And what we did was we solved this problem using exact diagonalization. We used what's called the Chivy ansatz, which the students, some of you who were at the class, saw this ansatz, because we know from experience it's pretty accurate. And then we also used matrix product states because we also looked at a strongly correlated system here. But I don't think I'll get too much into that because time is running up. But how much time do I have? 5 minutes. Then I'm just going to tell you the basic effects, and then I can do that in 5 minutes. So first we check whether it makes sense to talk about polarons when you're in 1D, you move along an edge. They're not quasi-particles in 1D, but for all intents and purposes, the polaron description, even though strictly speaking there are no polarons, it gives you predictions for the energies and so on, which are very close to the exact diagonalization and matrix product state calculation. So it's okay to talk about quasi-particles. And then here's the basic physics, and then I will just show you results from the interacting systems. So you can understand the basic physics from this simple model here. You have a chiral edge mode which has this linear dispersion here. You fill it up to, so you put the Fermi energy in the middle between the two bands of the topological insulator. So this edge mode is half filled. And then you put in, so it has this linear dispersion. You put in an impurity, which has this quadratic dispersion like this. And then you let them interact with each other. And then you see what happens. So it's all in 1D. So it's a very simple model. So you have the interaction, you have the dispersion of the impurity, and you have this linear dispersion of the half-filled bath. And here's what you get. So if you calculate the spectral function, so that is the energy of this impurity as a function of its momentum, it has this shape here. So if there was no interactions, it would just be a parabola with k squared over 2m. But you see that something happens when you turn on interactions. It becomes asymmetric, and you get this splitting here. You get a lot of features. And due to time, I'll just go through the basic things. Is you get an asymmetry, and you get a splitting here, two bands. And what is this? And then I will stop. Okay, so here is the same spectrum again. It's the energy of the impurity as a function of its momentum. So over here, you see nothing happens. When the momentum, when the impurity is moving to the left, it's basically unaffected by the interactions. It's just the usual parabola. And that you can easily understand from the fact that if the impurity has this momentum here, the only thing it can do is it can take a majority particle from inside the Fermi C to outside from in this branch here. it always costs energy, and the momentum is always, transfer is always positive, so it has to move in the opposite direction. So it's always, so this process, this scattering process costs energy in both for the impurity and for the edge modes. So it's off resonance, so basically nothing happens. If it moves on the other side, on the other hand, it can move down in momentum, and by creating an excitation up, this costs energy, but here you gain energy. So here something can happen, and you can actually convince yourself that at this momentum here, it actually starts to pay off to do this resonantly, and that's why you get this splitting. So you get this strong coupling when you're above this momentum, which is basically given by the velocity of the chiral mode. So when you are moving, when the impurity is moving with the group velocity of the chiral modes or larger, then it starts interacting with them strongly, just from these simple kinematic arguments. And here's a plot of the wave function, of the ground wave function as a function of momentum. When the momentum is negative, you're over here. The wave function is the momentum components of the wave function. It's basically just moving. The wave function is basically just the impurity moving to the left with the given momentum. There's a little bit of dressing, but not much. However, if you move with momentum equal to the group velocity, so if the impurity is moving with the group velocity or faster, then it just gets dragged. It just gets dragged along with the chiral modes, and it doesn't. Its main momentum is the same, so that it follows with the chiral modes. And this is this ground state here. So it cannot move faster than the group velocity of the chiral modes. This ground state is actually invisible, because what you're asking here is you're asking what's the overlap of this wave function here with the bare wave function. That's very zero. Imagine you inject it with a given momentum, so you cannot see this ground state. It becomes dark. But then what happens is that you get a repulsive and attractive polaron sitting above. So this chiral feature of this edge mode gives you this strong anisotropy in asymmetry in the spectral function of the impurity. You get these attractive and repulsive polarons, and yes, that's it. And then we tried this and then you can do the time. We tried many different things. We also did it for more realistic systems. So we did it for a churn insulator. The same effect happens, and we also did it for this Hofstadter-Bose-Hubbard model with strong on-site repulsion, and we also see similar asymmetric features. This is why we had to use this MPS calculations. And this work was done in collaboration with Nathan Goldman's group in Brussels. And with this, I think I'm definitely out of time, so I'll stop here. So yeah, thank you.
Thank you, Georg, for this very nice talk. Do you have questions? I do have a question.
Sorry, so I have two questions. The first one is, when you go to the few body physics,
Yeah.
you would tend to find some differences between even and odd number of particles. Can you comment on which is the properties of the state when you lose the 6 and go to 5?
So when you lose, if you go away from this magic shell case, but this is also what I want them to look at experimentally, then it's very different, because then you have a shell which is partially filled, and then you can start getting Cooper pairing. So you always get pairing, and then you want to. I'm thinking about even number systems here. You want to add an odd, so you want to do even odd.
Yeah, because you actually had a point where a resonance brought you from 6 to 5 particles, right?
Yeah.
So then what happens when you have 5? Like, do they want to pair? Some want to make like a trimer? Just can you comment a little bit on the state?
I think so, because if you want to go from the magic shell, and then you want to remove a particle.
Yeah, because that happened in your experiment.
Yeah,
right?
that corresponds to breaking a Cooper pair. So you pay, but it's okay. So that if you just removed it, if you just remove it from the shell, then that would cost you delta in energy. But what they did experimentally was not that. They actually excited it up to. They don't just take it away from the shell. They actually excited 2 shells up, and then it escapes the trap. So this energy here is basically 2 times h bar omega plus some pairing energy. Because you break a pair and then you have to excite it twice times omega.
Awesome, thank you. And if there are no other questions, this one? Oh, no.
Rosario, I think you have.
Could you please comment what about the importance of the size? So you first talk about the Cooper pairing, and you precisely this slide, and then at the end you talk about these edge modes. So how important is the size of the system when you talk about these edge modes? Because what we know is that in the thermodynamic limit is more. So the important thing is that the area is much. The ratio of the area among the volume goes to 0, and in that case, so the surface is not important. But what you said, as I understood, that the important thing in this case are these edge modes, or perhaps I missed something.
I mean, so I didn't worry so much about, well, actually, that's actually, so in these exact diagonalization calculations, we also compare exact diagonalizations of few body systems with the thermodynamic limit, but there we never tried to examine. We were always trying to hit the thermodynamic limit, so we were trying to see. So I guess what we saw was that again already for 10 particles in a strip geometry. I can't remember how big they were, but I mean, as you know, if the edge state starts to overlap, if the system is not large enough, then you start getting they start to become gapped. I think this is also what Jacob was talking about yesterday. So the general thing is that if you have to make the system so large that the edge states don't overlap on opposite sides shells, or opposite sides of the sample. And this in principle we could examine with our exact diagonalization, but we didn't look at that. We were always trying to make them as large as possible. But yeah, so we didn't look at we were not interested in few body physics in that case. Yeah.
Perhaps one more question.
Thank you. When you were talking about the polarity on collision, in the example you said, oh, if you have a BC and you have like a red atom traveling, my question is whether the BC part is important. I mean, why did you mention a BC? Is that part of, do you need that?
It's because it's very unpedagogical. It's because we talked about Doppler broadening this morning.
Okay.
So there's no Doppler broadening in this.
Okay, but
so I'm assuming that all the blue atoms have 0 momentum. They're just sitting in 0. They're in a BEC.
Okay.
So it's just because I discussed with. So how would we discussed this morning?
Okay.
We talked about you're not condensed.
Yes.
So I'm not taking into account the thermal distribution of these blue atoms. Yeah, I'm assuming they all. So what I'm going to do in this theory at some point, it's not visible here, but at some point I'm just going to say this G, it contains the square root of the condensate density times the coupling strength, but there's no momentum distribution in the blue atoms. They just sit at 0 momentum. Okay. And then the momentum you end up with, if you see in all the conditions, you see there's no broadening. I'm ending up in a very specific momentum, which is the momentum coming from the photon minus the momentum from the classical beam. So they are like this.
I mean, I wonder if could you just say if your experiment is fast enough that the motion doesn't matter, then it's also fine. I mean, is there?
I don't know. I'm confused about this statement.
Okay.
We have to talk about this. I mean, think that the motion doesn't matter, and
somehow
it. Yeah, maybe I don't know. I don't know how to. You have to think about how to translate this into this language. Whether it means that they are infinitely heavy, or so the band dispersion is flat, or what it means. I'm not sure. Yeah.
Okay, but you're not using like interference, like matter wave interference or anything like that that really requires a BC. I mean, I wonder whether the BC part.
No,
is
the
essential.
BC here is just a convenience
Okay,
for us.
okay,
It's just
that's my
because
question.
it's no, I think if you have a thermal cloud here, which you do, you will have to you will get some thermal average of the so then the scattering will just be in this language here will just be you have to do thermal averages of
Okay.
momenta of the incoming polaritons.
Okay, thank you.
Let's thank our speaker again. Thank you very much.